welcome to my YouTube channel. And yeah, we still have Python, But anyway, welcome to this introductory part of programming. And I really do hope that you're going to learn something. Anyway, so let's just get right into it. Let me share my screen first. Okay, let's share our screen. Huh. Okay. So this is an introductory part of programming. So yeah, an overview of programming, the definition. Programming is the process of designing, writing, testing, and debugging computer programs. What I mean by this is that when you're programming, you don't just start by writing the code. It is the whole process whereby you have to start from designing and make sure that everything that you're going to need or exactly how you want the program to be should be like that. And then after designing it, that's when you start writing the code. When you're done with the writing the code, you start testing it so that you make sure that it is doing exactly what you want it to be doing. Then, of course, you're going to be finding that there are some things that are not actually working. So that's when now you get to debug and yeah, then you release it. That's basically what programming is. It's not just about writing the code, it's a whole process. So when you're programming, you need to think of the writing environment that you have. And a programming environment is basically the digital workspace where software developers create, test, and run their code. Like where the whole process now happens, the writing, debugging, and everything else. So this environment consists of text editors or integrated environments where now you're going to, for example, the VS Code, Visual Studio, Sublime, Notepad++. This is basically, we would think of it like a notepad where you're writing everything that you actually want and what you need. And the environment also consists of a compiler. This is, we would think of it like a translator, which is translating the normal language or the languages, whatever language that you're using. For example, as a Flutter developer, it means I will need a Flutter compiler or a Dart compiler rather, since Flutter uses Dart language. So it needs a compiler like Dart, Dart compiler, which is going to now translate whatever I've been writing to machine learning. Machine language. The next thing that the environment consists is version control. So this one is basically what you need to be tracking your code. Every changes that you're going to be making, and if you're collaborating with others, this is exactly what you're going to need. It is also going to have terminal. This is where now you can be doing some tests, or you give it instructions. You give your code instructions to say maybe you want to run it or anything else that you actually want to happen. And you also have libraries. These are predefined instructions and rules that come with the language or plugins that you have. So now, I've been talking about programming languages. What is a programming language? These are a set of rules or instructions that a computer can understand and execute. So you don't just say anything or write anything that is coming to your head at any given time. You actually have to have it in, say, there are instructions or rules that you have to follow. For example, how we use English. You cannot just come and say and push nouns everywhere and expect people to understand what you're saying. So now, same with programming languages. it has its own rules where you have when to use verbs or when to use nouns, pronouns, and stuff like that. So there are two types of programming languages. We have the high-level language and low-level languages. The high-level languages are those ones that that are close to human language. They are in English mostly, and you can actually understand, for example, what we always write in. So if you're using JavaScript or if you're using Java, you actually see that you are using things like print or things like package. So those ones are high-level languages. And then we have low-level languages, which are close to machine languages. You have to actually start making sure that you read them and learn them so that you understand exactly what they're saying, because they're close to what the machine language understands, the binary languages, ones and zeros. So high-level languages has four categories in it. We have the procedure language, object-oriented, which is the most popular one because it uses objects and classes. So the procedure one uses set of rules. It's just instructions that are there. And we have functional languages. These ones actually just use functions, mathematical functions. And then we have logical ones, logical languages. And yeah. So some of the factors that you should consider when you're choosing programming languages are the purpose of your program. Do you want to develop a website? Do you want to develop a mobile application? Do you want to develop a game, data science? So all these types of programs will actually determine the kind of language that you have to use. And also you have to consider ease of learning. There are some languages that are difficult than others. Because in as much as we have like JavaScript for web development, we would have something else, or we could use Python, Flutter for websites. But you have to choose the one that is easy for you to understand, for you to learn, and also stuff like that. You also have to consider resource and support availability. I remember last year, somewhere around November, December, I started learning Dartfrog, which is a backend language for Dart. But since I did not have enough resources, online resources, and also support, community support, I ended up leaving it. Not that I left it, but I just got, it was a bit extreme for me. So those are some of the things that you have to consider. I ended up going to C# instead because I know I have a community of people that I'm going to ask. I have other things that I just have all these resources that I can find. Whereas for Dartfrog, it's very, very difficult. Now, if you're just starting out in programming, it's going to be very exhausting for you and frustrating if you don't find answers that you're looking for. Because there could be other times that you actually go online. Say you go on Stack Overflow, or you go on Medium or Twitter or LinkedIn, and then you don't find any answers at all. You can just think that maybe this is not for you when it's just the programming language that you have chosen. So yeah, you have to also think about the resources and support availability. So now one aspect of programming that you have to take very, very seriously is data structures and algorithm, because it's going to give you the backbone of your program. So let's define them first. Data structures are a way of organizing and storing data to perform efficiently. It defines the relationship between data, the operations to be performed on the data, and the constraints imposed on these operations. What I mean by this is that when you're having your program, you actually have to think to say, what are the operations that are going to be performed on my data? If you're developing, say, a music player, what do you want people to be doing? Okay, they should be creating a playlist. Inside the playlist, they should be able to add their favorite songs or remove their favorite songs at any given time. So you will have to choose the type of data structure that actually allows you to do this, because there are some data structures very, very difficult for you to add or delete data when you have added it, or to sort or do other things that you have. So this is exactly why you have to take data structures and algorithms very, very seriously. Algorithms, on the other hand, they are step-by-step procedures that are designed to perform a specific task or solve a particular problem. So they're just trying to give you a roadmap or a way forward for you to see or for you to solve a particular problem or for you to develop your program. And yeah, so some of the data structures that we have arrays. So an array is a linear data structure that collects elements of the same data type, stores them in adjacent memory. What I mean by this is, so we have here, this first one is data type. We have data, which is of data type integer, a number that is in here. The first one is 2, the second one is 4. So they are stored in an adjacent memory with this line that is demarcating the two data locations or data memories that we have. It has the ability to access elements by their index position or position. The indices are now labeled down here. So you can notice that the indices are starting from 0. And then you go to 1, 2, 3, and so on and so forth. That is how indices are. So you cannot start from 1. Those are the rules. You cannot start from 1. You have to start from 0. So for example, if you were to think that what is the position of 10? It means that this one is on position 2 and not position 3, according to the indices that we have here. So basically what arrays do, they offer a straightforward way to organize and manage collections of data. So like you just have this one that is straightforward, that is just there, like it's just a line, a linear data structure, like it's just giving you a linear adjacent memory. So yeah, that's about it. So in arrays, you like you see here, you can perform a different tasks, so you can use them differently. So one of the things that you can do are searching, common things that you're going to be doing in an array. So searching in arrays, this is just finding a specific item in the array. There are 2 algorithms that are used when you're searching in an array, which includes linear search and binary search. So in linear search, you check every item in the array one by one until the desired item is found. So for example, in this one, if we're looking for 15, and then you're using and then you're using linear search, it means you're going to start from index 0 to look for 15. And then it goes to 2. And then it goes to the first one, which is 2 here, and then it checks it if it's 15. So obviously, no, it's not 15. It goes to the next one, which is 4 here, and then it checks it again to see if it's 15, and then if it's not, it goes on and on until it finds it. So when it gets to index 4 here, which is exactly where our data is, so it gives you the desired results that you were looking for. So for example, if you're looking for the number to print 15, to print the index of data 15, it's going to give you to say, oh, 15 is on position 4, which is exactly how it is here. So this one, linear search, is actually simple because it's just searching through the memory locations that are there. And yeah, but it can be very, very slow and exhausting if a larger array is there. For example, if you had, say, suppose you have an array of 101 indices, and then you're looking for 3, which is on the far end. So it has to continue the process. It has to repeat the process over and over again until it finds the 100 and like say 101st index, which is like very, very exhausting, and it can be, so your program can be very, very slow. That's why you have to look for something that is going to be very easy and also fast. The next one is binary search. This one works on sorted arrays. What I mean by this is, okay, so for binary search to work, first thing that you have to do is sort the array in ascending order. So the way that we have our array that is here, it means the first location that we're going to have, or the first data that we're going to have, is 2, and then we have 3, then 4, 5, 10, and 15. My apologies, I was swamped. I forgot to think to cover this. So yeah, but the idea is you sort this thing out. You have from the lowest to the highest, and then you find the middle of it. What binary search does is it only searches the data from the relevant side. Okay, you've seen that in the linear search, you search it from the beginning to the end. What this one does is after sorting it, you find the middle part of it. Now the average part, the middle part, if what you're looking for is greater than the midfield, then it searches in the upper side of it. Okay, so if we have 2 here, 3 here, 4, 5, 10, and 15, it means our middle is here, but then we don't know the middle number that is here. For us to find the middle number, we have to find the average, which is going to be 4 plus 5, 9 over 2, 4.5. So suppose we're looking for 2. 2 is obviously lower than less than 4.5. So we're going to look for it in the lower side of it, which is going to be this side. So instead of focusing on all the data that is in here, binary search is only going to work on the left side, which is the lower side. And then it will look for the data in only these 3 positions. And yeah, since it's just 2, it's going to find it in the exact in the first place. So basically, that is the good part about binary search, I would say. Since it's literally minimizing the amount of time that you're going to use, and it's going to give you like lesser problems, or your program is just going to be faster. So yeah, real world example, Amazon products. When you go on Amazon or any e-commerce platform, you find that they displayed a lot of products on there. Now, what happens here is that they put their products in an array. For example, they are having books. So they have an array of books, say maybe from A to Z or something like that. And so what happens is if you're searching for something, they will go to the exact product that you're looking for. If I'm looking for, say, Think Big product, it's going to search in that array, in the array of books, in the array, say maybe in T department, or array of T's of books. So it's going to search in all those products, instead of searching like the whole catalog that they have. Maybe they have hair, they have electronics, they have any other things that they are going to only go into that one array that they save the products. So that is how arrays are used, and how search algorithms are used in real life. The next data structure that we have is linked lists. So linked lists, these are linear data structures in which the elements are not stored at adjacent memory locations. So the elements are linked using pointers. This, for example, we have this part, which is the linked list. Now it has, every linked list has like two parts. We have the data and the address or the pointer, which is next in this case. So it has one part with the actual data that you want to store. For example, if you want to store, say, number 1, and then you want to have the second one, B or C or D, and so on and so forth. The next side of the memory that you have is going to have an address of the next thing that you actually want to have. Okay, let me give you this example. In a media player, sorry, I'm just still going to use a media player because that's the one that I'm seeing in my screen. Anyway, so if you have a media player and then you have this playlist that you have, you are going to store your music, or let's say you have an album that you like and you want to be listening to it. The memory, what linked list does, it's going to store the name of the song that is there, and then the next song that is there after the first one. If, for example, the first song that you have is Pink, and then the next song is maybe Green, yeah? The address that is going to be on the linked list, that on the first node of your linked list, is the name of the song, which is Pink, and the address of where to find Green, which is the next one. So what this one does is it has like different nodes. These ones are called nodes. Node 1, node 2, node 3, node 4. So for instance, here we have like 4 nodes. So every node has the data and the next. It's pointing. And this is how they are connected. They're just linked with pointers, which are like these arrows that are here. And yeah, unlike the arrays that we had, that they were just basically adjacent, like they were close to each other. Their memories were literally like next to each other. These ones, they will not be next to each other. You can choose to point to the other one, or because we have different types now. For example, we have the simply linked in, which are the ones that we just saw here. They just go straight. And then we have the next one, which is doubling. These ones go both ways. It points to, so on this one, we would have a different pointer that is coming from B to A. So this one, it means it has like 3 different parts. The first one is going to be pointing to the previous side, like where it's going to be pointing previously. So in the case of the playlist, you would actually maybe like to re-listen to a song. So maybe you were listening to Vinyo, and then the song has ended, has gone to the next one. Instead of if you were in an array, it means it would just be moving forward. But in this one, you have the power, or you can actually go back to say, no, I want to listen to the same song. So once you press previous, it takes you to the exact song that you were listening. This only happens because of linked lists. The nodes are not adjacent, but they have pointers. So when you click previous, the pointer is pointing to the address of the previous song that we're listening to. And if you click next, maybe you don't like a song, or you just do not want to listen to it at that particular moment, it's going to point to the next song that you actually want to listen to. And we have circular linked lists. This one now points to the way that now is here. Okay, so the first node that we have is the head, and the last one is pointing to now because there's nothing else that is happening that it's pointing to. For circular, it's going to point to this first one. So that's now the case with if you want to be repeating this album or the same song, something like that. So now, instead of it just stopping when the music is done or when the album is done, it goes back and starts the album again. It repeats everything over and over again. So basically, that is what happens in LinkedIn, and those are the types. So number three, we have stack. This is a linear data structure that follows LIFO principle. LIFO principle is says that last one in should be the first one out. So a stack is like, we would think of it like a type of plates in your house, really. Maybe you would have like a lot of mag plates, and then if you want to use a plate, you cannot take the one that is in the middle or the one that is at the bottom. You take the first, I mean, the last one that you stacked on it, like on the plates. So that is what happens. Or you could think of it if you were putting guavas in a container or something like that. So the one that is going to be on top is the one that you can pick to eat. So that's what happens with stack. It only has one end, so everything else goes out and goes in through it. So you can think of this one is used in undo and redo functionalities, since it's literally the last thing that, I mean, the last thing that you did, and you want it to be the thing that has to be done or undone. So if maybe we're writing your application later in say Word, and then maybe you've messed up the say the punctuations or something like that, you just undo. So whatever happened there is in a stack, because when you're typing, it's going to give you the exact the thing that is you. Okay, it's going to delete the last thing that you have written, and not the first thing that you wrote in your application. So that is what stack does. Some of the standard operations that we have in stack is push, and you have to make sure that when you're using these operations, you have these brackets. It's very, very necessary. Like I mentioned in area, that there are a set of rules that you have to follow. You cannot just say, oh, it uses push, and then you say you just write push or something like that without the brackets or anything else. It's not going to work. So anyways, so push, what push does is it sets. So if you want to put something in your stack, you say push A, B, C, D, E. You want to delete something, you say pop, and then it deletes it. Is empty, it's actually checking if your stack is empty or not. The next thing that you have here is queue. Oh, that one is supposed to be 4. So queues are is a linear data structure that follows FIFO principle, which is first in, first out. Yeah, like how you are in a queue. Say you're waiting for you're in a bank, and then you found people that are there. You'll be behind everyone else that is there. So the first one that is going to be served is the person that came first. So that's how queues in data structures also operate. It's very first in, first out. It has two ends that are there. So if you put something inside from this side, and then they are going to go out from the other side of the container. So basically, that's what happens. In real life, you can use it in waiting list for a single shared resource like a printer. For example, you're in a workspace with like different people that are using same printer. You can just basically print it from your office, and another person prints it from their office, and maybe 3 people are trying to print at the same time. The printer is going to start with the first person that commanded it to print, and then the next one, and then so on and so forth. And that's what happens in queues. The last data structure that I'm going to talk about is trees. So trees are a hierarchical structure that is used to present and organize data in a way that is easy to navigate and search. And so this is how a tree looks. Okay, you would think of it like how you, in a company, you have the CEO, and then maybe you have managers, and then you have any other stuff that is there. And usually that hierarchy goes like this, like the way the root is, or on here, the first one is going to be only one person on top. And then all the other managers are going to be next. It doesn't matter how many managers you have. Maybe you have two, maybe you have three, maybe you only have one. So after the manager, they could have other people that are below it. So trees work in an exact same way. For you now to start searching, that's why now you go here to say, oh no, I'm looking for a manager. So it means you're going to look for them in this category. So the first one that is on top, say the CEO, that one is called the root node. So all these are nodes. The first one is called the root node, and then the rest of the nodes are called child nodes. So it could have like a lot of children, a lot of child nodes that are below it, but only one root node. So one example that trees are used are, you would think of it, Google search. It uses one that is called TRIE, tree tribe or whatever. Anyways, so this one, what it does when you search it, it basically stores like number of words. It has about 26 children because every letter is in there. So when you search, you would actually notice that you would just go there and say code, but Google is going to bring you like a lot of pages that are talking about code. So what's happening here is that the word code is the one that is the root node, and all the other pages that have code in them, or they are talking about code, those are child nodes of code. So basically, this is how trees work. It's literally just going to bring you all the children that are in there. So yeah. Finally, some of the best practices and ethics in programming. Um, you have code readability. You should make sure that when you're writing your code, you just don't write it and say, as long as it's working, then that's it. No. Make sure that it's readable by you and also other people that are going to be reading it, because in the end there are going to be some other people that are going to be using it, maybe after you're long gone, or maybe while you're still there they just want to help you, or just for your own goodness. I mean, tech is always changing. You would actually want to improve, to add other things. So if you do not know how to read your own code, or if it's not readable enough, you end up wasting a lot of time, one, to try to understand the code, or to just drop it all together and start over again, and it's not good. The second thing is commenting. So this is complementing the code readability. Commenting basically helps you to have a readable code. When you're commenting, you will know maybe 2 3 years or maybe 2 weeks, hell, you actually forget that whatever you were writing, these comments are going to help you exactly what you meant. Or so it's really, really good for you to be commenting the code. Security. Make sure you write code that is secure enough. Do not play with hackers or anyone. People are out there trying to steal your data, try to mess up your programs or stuff like that. So make sure that your programs or your code that you're writing is secure enough. You have to have respect for intellectual property. Sometimes, or most of the times, we tend to steal code, maybe from an open source project or anywhere else, Stack Overflow and whatever. We have to be respecting intellectual property. Give credit where it's due. If maybe you saw my code and then you took it, give me credit. Respect that it is my property, and say that, oh, this code was and and yeah, but you get the point. You get the point. You should just respect intellectual property. So yeah, I think this is everything that I wanted to talk about. And yeah, thank you very much. Do not forget to like and subscribe. Yeah. Okay. Oh, thank you. Right now I can get questions Let me see. Thank you very much, Ability. Thank you. There's so much fire in the comments. Okay, you can ask me questions. I don't know. So if you don't ask me questions, I'll think that it wasn't you did not understand or something like that. Either you understood everything or you did not. Which one is it? Thank you very much. Thank you. Okay, right now, chat. Okay, so thank you very much for joining, everyone that is here. Looks like we don't have questions. So until next time, bye. Have a good night. Yes, that's true. That's true. Just here says just one comment. Make sure your code is self-documenting. Writing comment is good, but make sure your code is self-documenting. Yes, that's true. Sometimes we tend to get to comments because we don't even know what we're doing or we don't really understand. We cannot really document it. So now, one other practice that is there or that you should check out is documenting it properly. Make sure the code is self-documented. It's explaining itself, I should say. It should, when one person, when a person looks at it, when you're looking at it, maybe some other time in the future, you should actually know from the code itself to say, oh, this is what it was talking about, and yeah. Just make sure that it's self-documenting. It's make sure it's readable. Should just go back to that. Anyways, so have a good night, everyone. And I hope I'm going to see you again in the next live. Bye.